Bismillah and good morning. So today we're going to continue with our topic 24. We are going to move away from electrolysis, where we have looked at the discharge based on the factors that affect the selectivity. And then we've also looked at the calculations. So now we're going to go away from electrolysis and we're moving towards what we call an electrochemical cell. But before we look at the electrochemical cell, which is another type of cell, slightly different from electrolysis, we need to understand a few things first. The first concept that we want to understand is the electrode potentials value. So define the terms standard electrode potential. As you have picked up that I have mentioned the electrode potential values, basically the ones that are given in the data booklet. These are your standard electrode potentials. In bracket, it's sometimes called the standard reduction potentials, but we just call it electrode potentials or the E-note values. Now to understand the electrode potential, we must look at a half cell first. So a half cell is usually consisting of elements of the same type but in different oxidation number. Okay, so for example, here we've got a copper metal and a copper 2+ ion, which is in solution, aqueous form, whereas the copper is in solid form. So when these two species of copper, they're of the same element, but they have different oxidation states. When they are in contact with each other, there is actually an equilibrium being set up. Okay, so this is an example of a half cell. What is a half cell? A half cell is when we have a single electrode in a solution of its ions where either reduction or oxidation can occur. So it's one part of your electrode system. Okay, so what happens if we look at microscopically into this copper solid, copper metal, and the copper 2+ aqueous ions? There is an equilibrium being formed. Okay, and the equilibrium form is between the copper 2+ to form copper solid, which is the reduction process, and as well as the copper solid dissolving into copper 2+ into the solution. So essentially these two reactions, because they are at equilibrium, they occur at the same rate. It looks like there is nothing happening there because the forward rate and the reverse rate of reaction is the same. So even if you want to see more Cu2+ being formed, the same amount of Cu2+ is also being removed to produce copper solid. Okay, so the metal atoms from the rod enter the solution as metal ions, leaving their electrons on the rod. So that means this is an oxidation process. Ions in solution gain electrons from the metal rod and deposited as metal atom on the rod. So this is the reduction process of the copper 2+ to form copper solid. Okay, so just because we don't see anything that is observable, it doesn't mean that there's no reaction happening there. Okay, so at equilibrium, there is actually a potential difference. Another name for potential difference is voltage. Okay, there's actually voltage between these two species of copper. Okay, bearing in mind that the rate of electron gains, so that is the rate of reduction, is equals to the rate of electron loss, which is the rate of oxidation, as you would expect already, as I have mentioned earlier on. Okay, but how do we want to find this potential difference? How do we find the voltage? It is impossible to just, try to connect this to a voltmeter and to read off the value from the voltmeter. Okay, we cannot do that. But what we can do to measure the voltage between or inside this half cell, okay, between the copper metal solid and the copper ion, is by connecting it to another half cell. Okay, so if you imagine one half cell is connected to another half cell, we get a complete cell. Okay, so here's an example of one half cell, which is the system between the zinc solid and zinc sulfate. So the system that we are interested in here is the zinc 2 plus and zinc solid. Okay, the sulfate ions is just floating in the solution, and then we connect this half cell with what we call a standard electrode, right? So if we want to know the voltage or the potential difference of this zinc 2 plus zinc system half cell, we need to connect it to a standard hydrogen electrode. Okay, so the reference or the standard that we're going to use is called the standard hydrogen electrode. So the setup is that there is no power or no supply of current in this setup, because this is unlike electrolysis. Okay, this is what we call an electrochemical cell, where the equilibrium between the zinc and the zinc 2 plus is supplying the voltage. Okay, it supplies the voltage that travels in the circuit. Okay, so all we need is a voltmeter. We don't need a power supply. And this thing is called the salt bridge. Okay, the salt bridge connects the two half cells together, which we will look at again later on. So here's an example of a zinc 2 plus and zinc half cell, and it is attached to a reference electrode, what we call a standard hydrogen electrode. So standard hydrogen electrode is also a half cell. It must contain the same element but at different oxidation state. So here we must have a hydrogen plus ions in the solution, and we must have a hydrogen gas supplied through the inlet. Okay, we'll talk about this metal later on. That is our electrode actually, and it's an inert electrode. So that brings us to the next section, which is the standard hydrogen electrode. Okay, we're now skipping page. We move on to page 9. So I will revisit page 8 later on. Okay, so for this learning objective, you are to describe the standard hydrogen electrode. Just like any other half cell, the hydrogen electrode, or our reference electrode, is also a half cell that contains equilibrium system. Okay, so the system is between hydrogen gas and hydrogen ions, right? They're the same element, but different oxidation state. Here, the oxidation state is 0. Here, the oxidation state is +1. Now, even though that it is a reference, even though that the value, the electrode potential that we take of hydrogen is 0, because we make it as a standard, there is actually an equilibrium happening here. Okay, so the rate of oxidation and the rate of reduction in this cell, in this system, is the same, equal. Okay, the standard hydrogen electrode is one of the type of half cell that can be used as a reference electrode. So you need to understand what makes up the standard hydrogen electrode. So first things first, we need a hydrogen gas. Okay, hydrogen gas will be supplied, as I said, through this inlets. Okay, so that's where your hydrogen gas comes in. You need to have a hydrogen ions. Hydrogen ions are in aqueous solution. So that means your solution here must contain H plus, whether we're using acid, HCl, monoprotic acid, or a diprotic acid, H2SO4. The most important thing is that its condition must be standard, because we call it a standard hydrogen electrode, right? And the standard condition is the concentration of H plus must be 1 mole per dm cube. Okay, so that's our first condition. The second condition is our pressure, because we've got a gas here. Therefore, our pressure must be standard, which is at room pressure, atmospheric pressure, 100 kilopascal or 1 times 10 to the power 5 pascal, or 1 atmosphere. It's the same thing. Okay. And then lastly, if your concentration has to be standard, your pressure has to be standard, your temperature must also be at room temperature, which is 25 degrees Celsius or 298 Kelvin. Okay, so you have all of this in your notes on page 9. Okay, so all the potential of any half cell are measured by comparing their potential to that of the standard hydrogen electrode. And because our standard hydrogen electrode, also called SHE, is used as a reference, we assign the voltage or the potential difference to be 0 volt. All right, so that means all the values that you see here, the standard electrode potentials, these values are all when the half cell is connected to the SHE, standard hydrogen electrode. Okay, so that's what it means. Another thing that I forgot to mention is the platinum electrode. Why do we have a platinum there when we've already got whatever we need? Okay, hydrogen, check. Hydrogen ions, check. Now the platinum, the function of the platinum electrode is to make sure, to ensure that the hydrogen gas here and the hydrogen ions have contact with each other. Okay, so to write that down, where is it? Let me just find it shortly. Okay, so the platinum electrode is in contact with the hydrogen gas and hydrogen ions. Okay, so these two things need to touch each other, and the platinum is like the electrode. Platinum is like the middle person for the hydrogen gas and the hydrogen ions to mix. Okay, so these are the conditions that I've mentioned already, and yes, it's given to you. Not sure if this is given to you in the notes. It is not. In your notes, you're just okay. Right, so I'm just gonna go through this quickly again. The standard condition for your standard hydrogen electrode is that the pressure needs to be at atmospheric pressure for the hydrogen gas. The concentration of the hydrogen ions need to be at 1 mole per dm cube. and you use an inert electrode. So the reason for this platinum electrode is to allow close contact of hydrogen gas and hydrogen ions in solution so that equilibrium can be established quickly. The reason why we use platinum is because it's inert and it does not take part in the reaction. Okay, you don't have this information, not word by word, but it's the same thing that you have on your notes. Okay, right. So what is electrode potential and what is standard electrode potential? Electrode potential is the potential difference or the voltage measured for a half cell compared with another half cell. Okay, so this is one half cell connected to another half cell. Usually that other half cell is a reference. So the definition of a standard electrode potential, which is mentioned in your learning objective, and you have to learn the definition. It is the potential difference. Do I have it here? The potential difference or the voltage of a half cell measured relative to the standard hydrogen electrode half cell at standard conditions, which is room temperature, room pressure, and standard condition concentration of 1 mole per dm cube. So here is the same diagram. Okay, you can see that one half cell is connected to another half cell via a voltmeter and a salt bridge. I will explain the function of a salt bridge later on. So it does not necessarily mean that the standard hydrogen electrode always have to be on the right side. Okay, we can also have a standard hydrogen electrode on the left side. The most important thing is because you are supplying hydrogen gas, you must make sure that you are using a tube. Okay, you don't just pump hydrogen gas and expect them to just dissolve and mix with the solution. You have to insert the tube halfway through the solution so that your hydrogen gas will eventually get contact with your H plus with the help of the inert electrode like platinum or graphite. And then the other half cell, it will depend on what system you are looking at. Okay, either you're looking at, here is the Fe2 plus and Fe system. You can also look at a half cell that contains the same type of element but in two different oxidation states like copper Fe2 plus and Fe3 plus, right? You can have that as well. And if you want to measure the voltage for the equilibrium of Fe2 plus and Fe3 plus system, then you need to connect it to a standard hydrogen electrode. Okay, so these are the standard electrode E-note values for all half cells that are relative to the standard hydrogen electrode. Even though it's not mentioned here, but you know that in order for us to get this value, we have to connect the silver plus silver half cell with an SHE, which is standard hydrogen electrode. Okay, now standard electrode potential. So describe the methods used to measure the standard electrode potential of A, metals or nonmetals in contact with their ions, B, ions of the same element in different oxidation state. Later on, calculate a standard cell potential. Okay, so there are two things here, standard electrode potentials and standard cell potential. There is a difference. Okay, measuring standard electrode potentials, there are three types of system that we can measure. The first type is the metal ion half cell. That means we've got a solid, which is your metal, and the metal ion is in the aqueous state. So for example, zinc solid, and we've got a zinc 2 plus. This is a half cell. Okay, the second type is a non-metal and a non-metal ion. So non-metal, for example, if we have a hydrogen gas, that's a non-metal. Okay, the other species must be of the same element but different oxidation state. So metal ion half cell would be H plus. Okay, or another example is if we use chlorine gas, which is a non-metal, and the nonmetal ion is Cl minus ion in aqueous state. The last one is the ion-ion half cell. When you have an ion-ion half cell, an example is copper plus and copper 2 plus. Okay, they can form an equilibrium system as well. Both of them are in the solution. So that means this electrode doesn't have a function, but you need it to complete your circuit, and therefore we just use an inert electrode for this setup. Okay, so the way you draw your half cell and eventually your whole cell, complete cell, is that you must look at the state of your two species. Is it a solid and aqueous species, in which case you will use this drawing? Is it a gas and aqueous species, which you will use this setup? Or is it aqueous ions and aqueous ions, where you would draw almost similar setup, but this time your electrode will be an inert electrode? Okay. So where am I going with this? Let's look at the first example, which is the metal/metal ion half cell. So metal ion is aqueous, metal is solid. We're going to look at the first example. This is now in page, hold on, page 10 of your notes. Okay, so there's a typo in your notes. It says example 1, to measure the standard electrode potential E note for zinc 2 plus zinc half cell. Change that into Ag plus and Ag half cell. So if you want to measure the half cell of silver plus and silver, you of course need to connect it to a standard hydrogen electrode. Okay, half cell of silver and silver ion, and this is the half cell of hydrogen ion and H2, which is also called a standard hydrogen electrode. Okay, let's talk about the Ag plus and Ag half cell first. I don't have the... If you look at the equilibrium system of Ag plus and Ag, you can see that it contains a silver species in +1, which is ion, usually found in aqueous solution. And the other species is a silver metal, which is a solid. We need to include that in our drawing or our setup. Okay, so we have silver solid as our electrode, and our silver ion is in the aqueous solution. So you would use any silver solution, whether it's silver nitrate, silver chloride. The most important thing is that you have that Ag plus supply, whereas your silver rod is your silver solid. Okay, pretty straightforward for the silver ions and silver equilibrium system, whereas for your hydrogen, just remember hydrogen also has its own equilibrium system, and it is this one, H plus and H2 gas. So H2 gas is being supplied into a tube. This tube is to trap any hydrogen gas that's planning to, leave or evaporate. So at least if you put it in a tube, there's no way that this hydrogen gas can escape, but to drop down and have contact with the solution contains H plus ions. Okay, so usually H plus has to be 1 mole per dm cube because that's the standard criteria. Most of the time, H plus, the source of H plus we use is HCl. Okay, if you use sulfuric acid, that means you need only 0.5 mole per dm cube of H2SO4. Okay, so H2SO4, the concentration of H2SO4 is 0.4 mole per dm cube, which is equals to concentration of H plus 1 mole per dm cube. Okay, if you're wondering why I need to only use 0.5 mole per dm cube, it's because of this. Sulfuric acid is a strong acid, 2H plus plus SO4 2 minus. Okay, so whenever you supply 0.5 mole per dm cube, the number of moles or the concentration of the hydrogen ions will double that number, which turns out to be 1 mole per dm cube. Okay. Okay, so the silver half cell is connected to a standard hydrogen electrode by a salt bridge. So this is my salt bridge, which is sometimes made up of KCl and KNO3. Once the circuit is complete, if you see this is a complete closed connected circuit, then it will read the potential difference value for silver ion and silver half cell system, and it turns out to be positive 0.80 volts. The function of the salt bridge is to complete the circuit by allowing the movement of ions between electrons and physically separating the two half cells. Salt bridge must be inert. So even though you're separating the two solution, the salt bridge helps to connect the two aqueous solution together so as to not mix the solution. Okay. All right, so the electrodes are connected to through a high resistance voltmeter. The voltmeter is there because we want to read the value. We want to read the potential difference. Okay, so the voltage that we read here is called the electromotive force or the EMF of the cell, E note cell. So don't worry about the E cell. I will talk about this later on. Okay, now this is unlike electrolysis where for electrolysis at the negative terminal cathode would have reaction, and at the anode where the positive terminal is, oxidation is happening. And in electrolysis also, we only need to learn about the factors that affect selectivity discharge. Here, in an electrochemical cell, we do not have that. Okay, the voltage is derived from the equations, from the reactions. Therefore, we need to look at the electrode potential values, E note values for each system. Okay, so you see here the system of H plus and hydrogen gas, the potential difference or the voltage is 0 as expected because we always take our hydrogen as our standard reference. Okay, and then silver ions and the silver half cell will read out 0.80 volts. Okay, in an electrochemical cell like this one, where you don't have currents or power supply, how do we decide who's positive and who's negative? Okay, for electrolysis, we know whichever electrode that is attached or connected to the positive terminal of the battery or the power supply becomes the positive, and the electrode that is connected to the negative terminal of the battery becomes the negative electrode, right? But here we don't have that. We don't have power supply. We don't have battery. So how do we know who is positive and who is negative? Simple rule. The most positive E note values will become the positive pole or the positive electrode. So between the hydrogen half cell and the silver half cell, we see that the silver is more positive, plus 0.80 volts. Okay, so automatically the silver half cell becomes your positive terminal, and the most negative half cell will become the negative terminal. So in this case, your hydrogen is the negative terminal. All right, and also the most positive E note will be most likely to be reduced. Okay, so the values that show the Ag plus ions with the most positive E note are more likely to be reduced. And therefore, this becomes the positive pole. Do I have this? Okay, so what this box is saying is that most positive E note becomes positive terminal, and reduction is also happening at the positive terminal. And the most negative E note will become the negative terminal, and oxidation happens at the negative terminal. The reason for this is because of the equation. A positive number suggests that forward reaction is favored, okay, which is the reduction reaction. And negative, well, or even though it's not negative, but it's the most negative between the two, will undergo oxidation. Okay. Right, that brings us to the next page. So in this case, the hydrogen half cell is the negative terminal and the silver electrode is the positive terminal. So I will just write here, most positive becomes positive terminal. And this is also where reduction is occurring. Okay, because forward, positive, moving forward, right? Negative, even though it's not negative, most negative system will become the negative terminal, and this is where oxidation occurs. Okay, we do not, I try not to use the word anode and cathode. If you remember, for electrolysis, okay, negative terminal is your cathode. All right, and this is where reduction happens. But for electrochemical cell, it's the opposite. is the oxidation reaction that occurs. Okay, the two half equations of the electrodes are, so we have to choose one equation for the oxidation reaction and the reduction reaction. So oxidation occurs here. That means we are looking at the reverse reaction, H2 to be broken down into 2H plus while releasing 2 electrons. So that's the oxidation reaction for the first one. Reduction is the most positive E note, which is the forward reaction, Ag plus aqueous plus electrons to form Ag solid. Okay, so I forgot to include the state symbol aqueous. So this is the oxidation equation and the reduction equation for the setup. Okay, so overall the reaction is simply just first making sure that the number of electrons match, and then only you can add both the reactants together and both the products together. So that means here you have to multiply by 2 so that you get 2 Ag plus aqueous plus 2 electrons to form 2 Ag solid, right? Once your electrons are balanced, then only you can combine them both like this. H2, so all the reactants will go on the reactant side, plus Ag plus aqueous, oops, 2 Ag plus, which is now red, I'll change that, plus 2 Ag plus aqueous. Now, I'll just show you the electrons first. Later on, you will see that they carry out. To produce 2H plus aqueous plus 2 electrons plus 2 Ag solid. Can you see that the electrons cancel out? So actually you don't have to write down the equation. The overall equation is H2 gas plus 2 Ag plus aqueous to form 2 hydrogen ions and 2 silver solids. Okay, and the E cell, the electrode potential value for this setup is positive 0.80 volts. Basically, you're just adding your E note of oxidation and E note of reduction. So E note of reduction is 0.80. E note of oxidation will be the reverse. Technically, you should be changing the sign, but here it's just 0, so you don't have to worry about that. Okay, now I'll teach you how to work out the E cell later on. So first, I just want you to copy this down. You can pause if you need more time to copy this down. Okay. Next is if we want to measure the half cell of a non-metal and non-metal ion half cell. An example for that is here. We've got bromine Br2 and Br minus system. In your notes, it says chlorine Cl2 and Cl minus. That's fine too. It works because you have a nonmetal element, which is Br2 or Cl2, and then you have a nonmetal ion, which is Cl minus if you're using chlorine, or Br minus if you're using bromine. So here I am using bromine. Okay, so bromine is supplied in gas state as well. So I have to introduce bromine through this inlet because it is a gas, therefore it must have a standard pressure, which is 1 atmosphere. Bromine half cell Br is Br2 and Br minus. So that means your Br minus has to be in the solution. So things like bromine, what can you like sodium bromide or potassium bromide, things like that, okay? As long as it is in 1 mole per dm cube. So this is the half cell of Br minus Br2 half cell. Since you want to know the value of this, the potential difference of this bromine, you have to attach it to the standard hydrogen electrode. So I've already gone through the standard hydrogen electrode where it also has its own equilibrium system. And the equilibrium system is hydrogen, B, C, D, E, F, that one, 2H plus 2 electrons to form H2 gas. Okay. So yes, you've got it here already. Okay, no need to copy. Okay. Again, to make sure that this setup is a complete circuit, you connect them through a voltmeter, and then in the solution, dipped inside the solution, there must be a salt bridge so that this whole thing is connected. The reason for the platinum here is just to make sure that the gas has contact with the ions in the solution. Okay. Right, same thing, same procedure. You write down the half system, the half equation for both systems, and then look at their E naught values, right? Which one is more positive becomes the positive terminal, and is this also the one that gets reduced, right? So I will write it here. Bromine is my positive terminal and hydrogen is automatically my negative terminal. So this is my negative terminal, different color. Negative terminal, therefore oxidize. Okay. So at the positive terminal, reduction is happening. So we should be looking at the forward reaction. Br2 liquid plus 2 electrons to form 2 Br minus. Okay, as for the negative terminal, oxidation is happening. So we look at the reverse equation. It's from H2 gas to produce 2H plus 2 electrons. Okay, so can you see that at the negative terminal where oxidation is happening, it releases electrons. Okay, so that means there are electrons here, and at the positive terminal, they require electrons. And where do they get electrons? They get electrons from the negative terminal. So Here, we are also looking at the direction of electrons. Direction of electrons is usually from negative to positive terminal. Now, these things are the things that will be covered again later on, but I'm introducing it to you early. Don't worry if you don't manage to catch up everything that I said, and most of the things are not in your notes. That is because it will come again later at one point in the notes. Okay, now overall reaction is when you add these two equations together, but bearing in mind that the number of electrons are the same and they have to be on the opposite side in order for them to be cancelled out nicely. Okay, so we've got H2 gas plus Br2 gas, Br2 gas, not liquid. Okay. Plus 2 electrons. You will see later on the 2 electrons will cancel out. 2H plus 2 electrons plus 2 Br minus. Okay. Don't know if you can see, but the 2 electrons cancel out. So overall reaction is that. Okay, I hope that makes sense to you. It is important for the electrons to cancel out. So on one half equation, the electron has to be on one side, and the other half equation, the electron has to be on the other side. Then only you would get oxidation and reduction equation happening. Okay, so this is a type of redox reaction. The hydrogen is being oxidized to hydrogen ion, and the bromine is being reduced to the bromide ions. The E cell for this is as it appears on the voltmeter, plus 1.09 volt. Okay, so I will teach you how to calculate E cell later on. Now, the last type of half cell that we can measure is the ion-ion half cell. So you can imagine same elements, but they are different oxidation numbers and they exist as ions. So an example for that is Fe2 plus and Fe3 plus. This is the half cell system for iron that is in different oxidation number. One is in +2 and the other one is in +3. You can also measure out the electrode potential for this Fe2 plus, Fe3 plus system, provided that you connect it with a standard hydrogen electrode. You complete the circuit in the presence of a salt bridge. So your Fe2 plus and Fe3 plus system is literally just this, okay? You need to make sure you have the Fe2 plus and the Fe3 plus in your half cell drawing. They're both in ions, so they can exist in the solution. And I don't know if you can see here, but there is a label called the platinum. That is the electrode, just so that the setup is complete and connected. All right, so that's why we use platinum, because it doesn't have any effect on the Fe2 plus and Fe3 plus system. Okay, so from the data booklet, we've got our Fe3 plus, Fe2 plus E naught values to be positive 0.77 volts, and the standard hydrogen electrode to be 0 as usual, because it is used as a reference. So from here, same thing. E node that is the most positive becomes the most, the most positive becomes the positive terminal. Okay, and this is also where reduction occurs. So the most negative becomes the negative terminal, okay, where oxidation occurs. So if we want to write that down, in the positive terminal, reduction is the forward. So the equation is Fe3 plus electrons to form Fe2 plus. Whereas at the negative terminal, which is your standard hydrogen electrode, the reverse is happening. Oxidation is happening. So oxidation is H2 to form 2H plus 2 electrons. Before I can combine them both, I need to check that my electrons are the same number. So that means I have to multiply this by 2. Okay, so it becomes 2Fe3 plus 2 electrons to form 2Fe2 plus. Okay, combining them both, it would be 2Fe3 plus 2 electrons plus H2 to form 2Fe2 plus 2H plus 2 electrons. So again, the electrons nicely cancel out. So you can tidy up your equation. The E cell for this is as shown in the voltmeter, which is 0.77 volts. Okay, so I know this is a lot of things, but I hope you can at least get something out of it, okay? Because you need this to develop the next theories that are coming in the next few lessons. Okay, so lastly, just before we go, I would just like to summarize. If E naught is positive or most positive, then reduction takes place at that electrode, and this is usually the positive terminal. If E naught is negative, or even though if it's not negative, but the most negative relative to the other half cell, then oxidation takes place at this electrode, and this electrode is called the negative electrode. We do not use the word cathode and anode, otherwise you will get confused. Okay, so sorry about that. There's not much calculation for now yet, but there's a lot of things happening. The way that the cell is drawn, the E naught values and how you can use it to determine whether an oxidation or reduction is happening. But I hope over time you are able to understand and get this concept. Okay, so just hold on to this because we will need this for the next lesson when we look at the E cell values, or what we call the electrode cell potential. Okay. Right. Assalamu alaikum and thank you, everyone.